In today's video, we study the kernel and range of linear transformations. So we define what they are. We also study what it means for a linear transformation to be an isomorphism, and thus what it means for two vector spaces to be isomorphic. And this idea is extremely important as it allows us to study a simpler vector space in place of a more complicated vector space. Let f from V to W be a linear transformation. The kernel of f is the subset of V containing all vectors whose image is the zero vector. The range of f is the subset of W containing all images of vectors in V. What we're going to do now is find the kernel of a linear transformation, specifically transformation defined by T of V is equal to this 2 by 3 matrix times a 3 vector. All right, so what we're going to do is we're going to say let V be a 3 vector. So it's an arbitrary 3 vector ABC. Right, then T of V. 1, -1, -2, -1, 2, 3. Right, this matrix times the vector ABC. Right, so from matrix multiplication, remember this is going to give us A minus B minus 2C, and then negative A plus 2B plus 3C. Now, in order for V to be in the kernel, this has to be the R2 identity, so just the 0, 2 vector. Notice, of course, this gives us a system of 2 linear equations and 3 unknowns, rather, sorry. So A minus B minus 2C has to equal 0, and negative A plus 2B plus 3C also has to equal 0. Right, now recall when we do this, we set up our coefficient matrix. And notice in this case, the coefficient matrix is the matrix that we're multiplying the vector by. We're just supposed to RREF this. Doing so will yield this matrix. Now, just representing this back as a system, A minus C is equal to 0. A plus C is equal to 0. Right, so of course notice that this means A is C. I'm sorry, this A here should have been a B. And B is equal to negative C. So C itself can be any real number. Therefore, the kernel of T is the set of 3 vectors of the form R, negative R, R, such that R is a real number. If f from V into W is a linear transformation, then the kernel of f is a subspace of V, and the range of f is a subspace of W. In other words, the kernel of a linear transformation is a subspace of its domain, and the range of the linear transformation is a subspace of its range, its codomain. And so, to prove this, let's first prove kernel. Remember, there are three things we have to prove. It's a non-empty subset. In other words, it contains the identity. 2, it's closed under addition. 3, it's closed under multiplication. Well, by definition, we already know that the kernel of F is a subset of its domain, right? So it's a subset of V. Also, recall that we have shown that f of the identity in the domain is equal to the identity in the codomain. So this means that the identity in V is guaranteed to be in the kernel. Now let's let U and V be any vectors in the kernel of F. And we're going to let's let C be some real number. Then, if we look at f of u plus v, this is f of u plus f of v by definition of being a linear transformation, which equals (0w plus 0w), and recall that that is just 0w. And if we take a look at f of c times u, this is, again, by definition of linear transformation, c times f of u, which will be c times the identity in w, which, again, recalls just the 0 in w. Therefore, what we've just shown is that u plus v is in the kernel of F, and c times u is in the kernel of F, which means that the kernel of F is a subspace of u. I'm sorry, is a subspace of V. Next up, looking at range. Again, by definition, the range of F is a subset of its codomain. Also, again, since we've already shown that if we transform the identity in V, we get the identity in W, we know that the W identity is in the range. Now we're going to say f of u and f of v are in the range of F. And we're going to say C is a real number. Then we know that u and v have to be in V, which of course means that u plus v is in V. Thus, what we have, f of u plus f of v is equal to f of u plus v, right? Because f is a linear transformation. And this has to be in the range of F. Right. Also notice that CU has to be in V. Right. This implies that C times F of U, again, by definition of linear transformation, is equal to F of C times U. This is also in the range Therefore, the range of F is a subspace of W. Let F from V into W be a linear transformation. The dimension of kernel of F is called the nullity of F, and the dimension of range of F is called the rank of F. Right? So these are corresponding to rank and nullity of a matrix. What we're going to do is now determine the rank and nullity of the linear transformation from R5 to R4 that is given. We do this by first finding a basis for both the kernel and range, and then using that basis to determine rank and nullity. First, let's look for nullity, right? Kernel of T. So we're going to take some arbitrary vector in R5. And determine when this will transform into the identity in R4. And so remember then, we're going to take T of X. Right, which is this 4 by 5 matrix times our vector. This will give us a 4 vector. x1 plus 2x2 plus x4 minus x5, 2x1 plus x2 plus 3x3 plus x4, negative x1 minus 2x3 plus x4, 2x4 plus 8x5. To determine when this is in the kernel, we just set this equal to the 4, 0 vector. Proceeding as we have before, we take our coefficient matrix, row reduce it, And now notice column 3 and column 5 are both columns that do not have a leading 1. This means that these two variables, x3 and x5, are free variables. And every other unknown can be written in terms of these two free variables. So our kernel of T will equal negative 2r plus s, r plus 2s, r, negative 4s, and s. This set such that both r and s are arbitrary real numbers. Now what we're going to do is we're going to say, well, let k be some arbitrary vector in this kernel. That means that k would have to have this form. Which we can write as r times negative 2, 1, 1, 0, 0, plus s times 1, 2, 0, negative 4, 1. It is easy to see that these two vectors are linearly independent, and they also span our kernel. So a basis for our kernel will be this set. Now, let's look for the nullity, right? So remember, nullity is the dimension of the kernel, and dimension, recall, is the number of vectors in any basis for the vector space. So this implies that our nullity is equal to 2. Now we just have to do the range. Right, so recall by definition, the range is just the set of vectors in the output, that the transformation outputs. Well, we already saw that. Right? All of our output vectors will look like this. So range of T is the set of vectors of that form. where all of the x's, so x1, x2, x3, x4, and x5, are real numbers. What we're going to do is take some arbitrary vector r in the range. Right, that means that r has to have that form. Which we can now write as a linear combination, specifically this one. x1 times 1, 2, negative 1, 0, plus x2 times 2, 1, 0, 0, plus x3 times 0, 3, negative 2, 0, plus x4 times 1, 1, 0, 2, plus x5 times negative 1, 0, 1, 8, Now it is obvious that these 5 vectors span our range. We just have to determine if they're linearly independent. Well, notice that these 5 vectors form the columns of this matrix up here. And we've already row reduced it. And we saw that the 3rd column and the 5th column did not have leading ones, which means the 1st, 2nd, and 4th vectors of our linear combination are linearly independent and thus form our basis. Right, so this set of vectors defines a basis for the range. Since there are 3 vectors in the basis, that means that the dimension of the range is 3, which implies that our rank of T is equal to 3. A quick observation of this last example will show Theorem 2, which says let f from V into W be a linear transformation from an n-dimensional vector space V into any vector space W. Then the rank of f plus the nullity of f will equal n. In other words, the rank of our transformation plus the nullity of our transformation will always give us the dimension of the domain. Now, this is offered without proof, right? This is our corresponding theorem. Remember, with rank and nullity of a matrix, where we said that the rank plus the nullity of a matrix always gave the number of columns of the matrix. Let f from v into w be a linear transformation. If f of u equals f of v implies that u is equal to v, then the transformation is said to be 1-to-1. If range of f is equal to w, then f is said to be onto w. Right, these terms should be familiar. Right? These are the same terms studied in pre-calculus when you're looking at functions, right? You could have a 1-to-1 function and an onto function. And by the way, their meanings are exactly the same, right? Which makes sense because f is a mapping, which is just a function. A linear transformation is 1-to-1 if and only if its kernel contains only the identity. First, assuming f is 1-to-1. We know that f of u equals f of v must mean that u is equal to v. Now, we also know that f of 0 is equal to 0. So, for any vector w such that f of w is equal to 0, we must have w is equal to 0 because f is 1-to-1. This means that the kernel of f contains only 0. Now conversely, we're going to assume that the kernel contains only 0. Consider vectors u and v such that f of u is equal to f of v. What we must do is show that u is equal to v. Then, f of u equals f of v. This implies that f of u minus f of v is equal to f of v minus f of v, which is equal to 0. All right, we know this because we've already shown that the range is a subspace. Right? So since f of v is in the range, its additive inverse minus f of v must also be in the range. And when you add them together, you must get 0. What we now have is f of u plus -1 times f of v is equal to 0. By definition of linear transformation, this of course means that f of u plus f of -1 times v is equal to 0. Again, by definition of linear transformations, f of u plus -1 times v is equal to 0. Which means that since the kernel of f contains only 0, u plus -1v has to be 0. This means that u plus -1v plus v would equal 0 plus v, which is just v. which means that u plus 0, right? So negative 1v plus v has to equal 0, is equal to just u, and that has to equal v. So therefore, we've just shown that u is equal to v, which means that f, by definition, is 1-to-1. So we've now shown that f is 1-to-1 if and only if its kernel contains only 0. A linear transformation, f from v into w, that is 1-to-1 and onto, is called an isomorphism. Moreover, if v and w are vector spaces such that there exists an isomorphism from v to w, then v and w are called isomorphic to each other. Now, this is important. Vector spaces that are isomorphic to each other behave exactly the same way. In other words, if v and w are isomorphic, then any property of v is also a property of w. We now answer the obvious question, which is, are two vector spaces of the same dimension isomorphic? And they are, and we're going to show that right now. All right, so assume that v is isomorphic to w, where the dimension of v is equal to n. What we have to show is that the dimension of w is also equal to n. Well, then there must exist a linear transformation, call it f, from v into w, that is both 1-to-1 and onto. Since f is 1-to-1, we must have the dimension of the kernel being 0. Which means that the dimension of the range, which remember is equal to the dimension of our domain V, equaling n. However, since f is onto, the range is equal to the codomain, in this case w, which means that the dimension of w is also equal to n. Now what we have to do is assume that the dimensions are equal. So let's say dim v is equal to dim w, and let's say that equals some n. We have to show that there exists an isomorphism between v and w. So what we're going to do is say let b equal v1 to vn. Define a basis for V and B prime equals the set W1 through Wn, define a basis for W. Therefore, for any vector in our domain V, there exist constants C1 through Cn such that V is this linear combination. I'm sorry. These should be V's, not W's. What we do is we define a linear transformation let's call it L from V to W as L of V equals C1W1 plus so on and so forth plus Cn Wn. In other words, we write L of V as a linear combination of W's using the exact same constants. Now, this is both one-to-one and onto, and the verification of this is left as an exercise, which implies V and W are isomorphic. Right, so what we've shown is that vector spaces are isomorphic if and only if they have the same dimension. In other words, all vector spaces of the same dimension behave the same way. So if we're given an n-dimensional vector space, and we're asked to show that a property holds in that vector space, it would be simpler just to show that it holds in Rn, the set of n vectors, because the set of n vectors is a lot easier to work with. A linear transformation f from V into W is said to be invertible if a transformation G, W into V, called an inverse of f, exists such that G of f of V is equal to V for every V in V, and f of G of W is equal to W for every W in W. Again, this idea should be similar, as this is exactly how an inverse function was defined. And again, a linear transformation is simply a function. If a linear transformation is invertible, then its inverse is also a linear transformation. So let f from V into W be a linear transformation with inverse G W into V. At V1, V2, B, and V, such that f of V1 equals W1 and f of V2 is equal to W2. Also, let C be a real number. f of v1 plus v2 would equal w1 plus w2, which implies that g of w1 plus w2 is equal to v1 plus v2, which is equal to g of w1 plus g of w2. And f of cv1 would equal cw1, which implies that g of cw1 is c times v of 1, which equals c times g of w1. Therefore, G is a linear transformation. If a linear transformation is invertible, then its inverse is unique. So this is offered without proof. And finally, let f from v into w be a linear transformation. Then f is invertible if and only if f is 1-to-1 and onto. In other words, only isomorphisms are invertible. Now, since f of g of w is equal to w for all vectors w in w, f is indeed onto w. Now let vectors v1, v2 be in v, such that f of v1 is equal to f of v2. Then we must have g of f of v1 equal to g of f of v2, implying that v1 is equal to v2, which implies f is 1-to-1. Conversely, if f is 1-to-1 and onto, then for every vector w in w, there exists a unique v in v, such that f of v is equal to w. Now let g from w into v be defined to assign that v to the corresponding w. That is, g of w is equal to v whenever f of v is equal to w. Which yields the formulas from definition number 5, which was the definition of invertible. Therefore, we conclude that f is invertible. And that concludes today's video on kernel and range of linear transformations. In the next video, we conclude our look at linear transformations by studying how we can represent a linear transformation as a matrix. As always, I thank you so much for watching, and I will see you all in the next one.